This video is going to go into how can we describe gases quantitatively, so with numbers, and for this one, the main four variables that we can describe gases with are pressure, volume, temperature, and amount. And so you'll see me abbreviate pressure with P, volume for V, T for temperature, and then amount is going to get the symbol N. The unit for amount is going to be in moles, so how many particles. So if it helps you to remember that N is like number of gas particles, but it has to be in moles if we're going to do anything with numbers. And so again, we're going to really focus on being able to visualize the gas particles and what they are doing this unit. And so we can also put numbers to that. And the last video went into how we can not put numbers with it, so do the qualitative, but this one is going to be more how we put numbers. I like kind of the analogy of a billiard pool table for understanding gases and the variables. So if you think about the boundary, the container size, as like how big the pool table is, that's going to be our volume. So is it a fixed? What we really care about for volume, is it a fixed container or is it flexible? So is it rigid or is it flexible here? And so how many balls are on the pool table or how many gas particles are present, that's going to be moles. And then how fast are the gas particles moving? So assuming that without you hitting the balls on a pool table that they would be moving, but how fast they are moving would be then the temperature. And then the most important one is, I think that for the visual, is pressure, okay? And so pressure is created when particles hit the walls of the container. So that's going to be the, if you think about the pool balls colliding, that is what creates pressure and how we can measure pressure. We're going to dive into each of these, starting with pressure. So, as I was just kind of saying, that gas pressure is created by molecules of gas hitting the walls of the container. That's the visual image you need to have in your mind when you're thinking about pressure, is them hitting the walls of the container. Okay. Another definition of pressure is the amount of force exerted over an area. So if you think about pressure is force per area, that's a more mathematical term for it, but that's how pressure gets measured, and really that force is created by particles hitting walls of the container. And then how big that container is, the area, is going to determine how high or low the pressure is. Now, pressure has a lot of historical units, and so you just kind of have to learn them because they all get used in different contexts, and there's even more than this, but these are kind of the big ones. So if we're going to standardize pressure, and we look at that as like, what is normal Earth's atmospheric pressure? So atmospheres is a comparison value, and it's what's used to scale all the other units for pressure. So we give atmospheric pressure a value of 1, and that is the average pressure of our air or Earth's atmosphere at sea level. So it's already pretty close to sea level, so most days our air pressure is close to 1 atmosphere. But if you were in the mountains or at a lower elevation in a valley or under the sea, then you'd have a different pressure. Kilopascals is the SI unit for pressure, so it's the international one. It's the one that gets most used in scientific literature and classes, and it'll get abbreviated as kPa. And there are 101.3 kilopascals in 1 atmosphere. That's a conversion factor that's going to allow us to go in between those units. Millimeters of mercury, it's abbreviated as mmHg. It's also known as a torr from the Italian scientist who originally measured mercury, columns of mercury, in studying pressure relationships. And so what they have found is that if you have a column of 760 millimeters of mercury, which is the same thing as saying 760 torr, as a nod to the Italian scientist who did this experiment. That's equivalent to an atmospheric pressure. So if you had a column of mercury and it was 706, or that's how high it would be under normal atmospheric conditions. You live in America, so we don't use millimeters most of the time. So if you were to listen to the news channel and they were talking about the pressure, they're going to use barometric pressure, but the units, if you pay attention to them, are going to be in inches of mercury. And there are 29.92 inches in an atmosphere. So another conversion factor. The last common unit that gets used quite a bit is pounds per square inch. It's a big unit in industry, and that's going to measure like the weight, the force in per square inch per area. So I like this unit because it kind of helps you visualize that force over area, because it's like how many pounds of particles are there per square inch, and 14.7 psi is equivalent to 1 atmosphere of pressure. So all of these are equivalent to each other, so you can convert between any one unit and any other. I just wrote them in the order that I showed them in, but you can go from any one to any other. It'd be like saying, you know, there's 5,280 feet in a mile, there's 1.61 kilometers in a mile. You could go from kilometers to feet because you know the equivalency. So we could go from atmospheres to millimeters of mercury. We could go from psi to kilopascal. All of them are equivalent to each other. Okay, so with that in mind, we're going to do just a couple conversions so that you can see the expectation for work for these using units of pressure. And this is what your introductory homework will have you do. So this first one, we have 725.0 torr, and we want to know how much pressure that is in psi, since it's more of a unit we'd be familiar with. Oh my goodness. Let's put the unit we want to cancel on the bottom and put the unit we want to go to on top, and then we're just going to fill in the conversion factors. So it says for every 760 torr, we'd have 14.7 pounds per square inch. And if you type that into your calculator, which I'm going to do as well, your calculator will display 14.023 ... We are going to get 4 sig figs, so 14.02 here would be our answer in pounds per square inch. You can kind of think, does this seem reasonable? 725 is a little bit less than 760, so our answer should be a little bit less than 14.7, so a little bit under 1 atmosphere of pressure. Okay, next example. A tank of oxygen is under a pressure of about 4.00 times 10 to the third kilopascals. And we want to get this to millimeters of mercury. So we want to cancel kilopascals and then put the unit we want to go to on top, because again, you can go from any unit to any other. You also do not need to memorize these conversion factors. I will give them to you. Just have to know how to use them. There are 101.3 kilopascals and 760 millimeters of mercury. 4.00 times 10 to the third is the same thing as 4,000 in standard notation, but I wrote it like that to show that we have 3 sig figs. And if you do this in your calculator will display 30,009.07 ... Now we're only going to get 3 sig figs. So how do you round 30,009 to 3? Because you can only write 30,000 in standard form with 1 sig fig or 5. So this is where kind of like 4,000 here. The reason I wrote it is 4.00 is I want to show these 2 zeros are significant and that last one isn't. That's why I wrote it in scientific notation. it's going to be the same thing here. We're going to write it as 3.00 times 10. We have to move that decimal place 1, 2, 3, 4 places, millimeters of mercury. So that's just showing you a couple conversions for pressure. You'll have a couple more to practice with on your own. The next variable for units and how we're going to measure it is volume, and just how much space the gas takes up, or which it's enclosed in. The most important thing we need to think about whenever we're studying gases is the gas in a fixed or flexible container? Meaning, is it a rigid container, or does it have some give? Does it have the ability to expand? So a balloon would be a very flexible container. An aerosol can would be very fixed, rigid container. A syringe would be flexible, for example. Unlike pressure, there's not very many units we use to measure volume. The main one is liters, but you will have to convert between milliliters and liters a lot, because when we plug volume into measurements, it will be in liters. And so again, it's worth memorizing that there's 1,000 milliliters in a liter. And then the other common unit is cubic centimeters, because that's just three-dimensionalizing a regularly shaped object. So remember that a centimeter by a centimeter by a centimeter is a cubic centimeter, which that's equivalent to a milliliter. That's actually how a milliliter gets defined. And so if they're equivalent, you can also say there's 1,000 cubic centimeters in a liter. So just don't be thrown off that that is a measurement of volume, three-dimensionalizing space. For temperature, to measure temperature, we need to measure the average kinetic energy. Well, in order to do that, we have to have it in Kelvin. Okay, so you guys are used to Fahrenheit and Celsius, but that is not going to fly when we're doing mathematical numerical problems, because again, the only temperature scale that is proportional to the kinetic energy, how fast those particles are moving, is in Kelvin. Okay, now degrees Celsius is what our thermometers are going to measure temperature, and I don't have any Kelvin thermometers, but so we're going to have to convert it to Kelvin, and to do that we just have to add 273. So they're the same size unit, you just have to add 273, so no multiplying here. So temperature Kelvin is equal to degrees Celsius plus 273. So if you were going to do this, you know, add this one plus 273, your calculator is going to display 310 Kelvin. Notice there's no degree sign with Kelvin. It's not degrees Kelvin, it's just Kelvin. So you just write 310. That 0 would be significant, so it'd be better to put that placeholder, that decimal there at the end, to show that that 0 is significant. And then if you had a problem going the other way, you just subtract. If you went from Kelvin to Celsius, you just subtract 273. A key conceptual understanding here is that doubling the temperature in Kelvin doubles the kinetic energy, but that's not true in Celsius. So let me just show you this, okay? Is that if you have, let's say, something that is 50 degrees Celsius, and say you double it to 100 degrees Celsius. If we add 273 to both of those, this is really 323 Kelvin, and then this would be 373 Kelvin. And that is not, like 373 is not 2 times greater. In fact, if we put them proportional, because right, like 100 over 50, right, it's going to be 2 times. Like it looks like, oh, I've doubled the kinetic energy. But 373 over 323 is really, we have only increased the speed of those particles by 1.15 times as fast. So if we wanted to double the kinetic energy, we could go from 50 Kelvin to 100 Kelvin. Or if we were in 50 degrees Celsius, which is pretty warm, and we wanted to double it, we'd have to get all the way up to 646 Kelvin. Okay, so just so that you are aware, in order to double how fast the particles are moving, you have to double that temperature in Kelvin. Just to end this video, some other terms frequently used for this unit that you need to know is STP. So that stands for standard temperature and pressure. And so if a problem says you're at STP, then you know that the temperature is 273 Kelvin or 0 degrees Celsius, and you're at atmospheric pressure. Okay, so you could be in any of those standard units for pressure. That's what STP stands for. And then the other common term phrase is room temperature. So if a problem says, hey, you're at room temperature in the scientific world means 298 Kelvin or 25 degrees Celsius. So that is where we will end this video, and this is a good introduction into the variables we're going to measure gases with and the units that are associated with them.